All right, welcome back. Just a quick reminder where we left off. Remember that we established that the object that goes here is A rho t, and the object that goes here is B rho t. And we've developed a set of differential equations for A and B. And now, today, we are going to solve those differential equations. All right, so here we have it. These are the differential equations. So let's attack, say, this one first. This one actually looks pretty easy, right? We just write b prime over rho b equals 0. And this implies directly that b dot equals 0. And therefore, that tells us pretty straight up that b is not a function of rho and t. B is just a function of rho. So this basically, all the information in here is b is a function of rho. So we've actually proven that at least the b part of this thing has to be static, right? Has to be static. It's not a function of time. So that assumption, and remember, that's a good point to make, right? If we had gone with the assumption in the beginning that the whole thing was static, what would have happened? Well, this term wouldn't be here, this term wouldn't be here, those terms wouldn't be there, this would have been 0, that wouldn't be there, all of this stuff would be gone. So the assumption of being static has a demonstrable effect on how easy it is to execute this proof, right? But, you know, in some sense, what we've done has already helped a lot, because knowing that b is a function of rho, we can eliminate this term and 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 this term. Well, I guess I should get rid of the whole term in that case, right? And this term, right? We can just get rid of those terms. So that substituting that fact into this has simplified things a lot, and get rid of that term too. Okay, so with that, let's move on. So here I've written down the differential equations that now face us with b prime being 0. Notice that what's interesting about this is the fact that b is not a function of time has actually removed all the time derivatives out of the situation. There's no dots left, and that's because the one place where a prime was showing up was right here, and it was multiplied by b prime. So I think that's just kind of interesting. So what's left over is only row derivatives of things. Still nonlinear, right? We still got this nonlinear piece, this nonlinear piece. But what we do now is we say, okay, how are we going to solve these four coupled equations? It's getting easier. And what we do is we are going to combine these two and try to eliminate more terms together. And the way we're going to do it is we're going to divide, let's see, I think we'll divide this one by A, and then we'll divide this one by B. And what will happen is you'll end up like this term and this term will both have, this one, if I divide by A, will have an AB in the denominator, and this one will have an AB, and those two will cancel when we add them, so that's good. This one here will have A, see, I'm dividing this by A, so it'll be A prime B prime over AB squared. If I divide this one by B, it'll be A prime B prime over AB squared. So it'll be interesting to see how does that, will that cancel though? No, it won't cancel. And the reason it won't cancel is because I got my sign wrong, right? This is a minus, so that should have been a plus, right? I know that this is, a lot cancels here, so I kind of know what to expect, right? So those two will cancel if I do the division I said. And then here, the same thing will happen. If I divide this by A, it'll be 4A squared B, and this will be 4A squared B if I divide this one by B, and those will cancel. And then I'll just leave these two terms. So the result of that work should be, let's see, I'll go over here and write that down. So if you just combine them, you end up with this expression, right? You end up with a prime over ab, b prime over b squared. And then, let's see, we factor out the b, right? So we end up with 1 over b. And then this is a prime over rho. Well, actually, I factor out a rho b, right? So 1 a prime over a plus b prime over b equals 0. Then, of course, this guy cancels, and you get a prime over a equals... I want to set this up for the product rule, right? That's what I want to do. When you see this structure, you think product rule right away, right? So you think that's a prime b plus b prime a equals 0. And now you're actually set up to reverse the product rule, and you can write down that's the same as a times b prime equals 0, right? Which tells us that a times b equals a constant. So that was helpful. Now, don't make the mistake, this is not a dot product here, right? I probably should, because we do use vectors in this course, that's ab equals a constant. Now, the reason that's important is because we've already established that b is a function only of rho. So if ab equals a constant, imagine that we had a rho as a function of t, b is a function of rho. That is a constant. That should be a number that never changes. But if you change t, and a is a function of t, then a is presumably going to change. So, but b can't change to compensate. So therefore, we now know that a is a function of rho, and now we have completely demonstrated that this is a static condition, right? Neither a nor b are functions of t, which means g mu nu is not a function of t, right? There's no functional relationship between the metric and t. So that's pretty cool. So we've proven that no spherically symmetric space-time can have a metric that's dependent on time at all. So that's really interesting. Okay, so that's important. And then, but we do learn another thing from this, right? We can now broker it to substitute away for a prime. So a prime is now minus b prime a over b, right? Now, so this is useful because hopefully, we still have a mess of differential equations to deal with, right? We still have, for example, this differential equation. That's still true. We did combine it and we learned these facts, but we still don't have the actual form of a. But we can substitute away for a prime in favor of b prime and a over b. So we're going to do that and hope that it simplifies. Spoiler alert, it does. So let me copy this. I'll go to another sheet and I will put it down, right? So we also have, so here is the differential equation. This is the substitution we're going to hope we can exploit. And the goal of the exploitation, by the way, is to get this term here to cancel with that term here, right? Just leaving these two terms. And so the trick is to realize you're going to substitute for just one of these two a primes, because if I do, I'll get a b prime and an a, but that a will cancel with the denominator. That b will make that a b squared, and these two terms will actually match and cancel. So just explicitly, this will be the substitution. And what you'll see is, right, this a here cancels with that a, leaving a prime, b prime, 4b squared, and the two signs cancel to become a positive sign, which will allow it to cancel with that term. So this term and this term will cancel. Actually, the way I should write it is this is the substitution, right? This is the after the substitution, this term becomes this, and it obviously cancels. So we can simplify. Let's just rewrite the differential equation now. It's a prime prime over 2b plus A prime over rho B equals 0. Phew. Now, we can simplify this, right? This can be, we can pull out this B, right? So that's 1 over B. Multiply by 2 and pull out B, right? So then we end up with A prime prime plus 2 over rho A prime equals 0. And that means that our differential equation that we got to work with is A prime prime plus 2 over rho A prime equals 0. So this is a first order ODE. It's a first order ODE for A prime, right? For A prime. So I could substitute A prime equals U just to make it completely clear. And that becomes U prime, this is a rho, not a 5. U prime plus 2 over rho U equals 0. And that becomes U prime over U equals minus 2 over rho. And then you integrate both sides, right? And you get log of U equals minus 2 log of rho plus a constant, right? But that constant can be, that constant is the log of something. So you take that constant into the log, right? So we're going to take the constant into the log and make it the log of rho times a constant, right? And so then you raise everything to the e, so you get u equals, this raised to the e is going to be 1 over rho squared, and then that there'll be a constant down here, but we'll just put the constant up there, right? Change the constant so it's in the numerator. So that is u, right? So that is the form of u. But u is equal to a prime, right? So that equals a prime. So now I have to integrate u. So the integral of u du equals the integral c over rho squared d rho. And I'll change my pen. And this is the definition of, that's a, right? And then this will have to be what? Minus 1 over rho, minus 1 over rho times some other constant. I guess I'll have to call that C1 because now I need to add a second constant, C2. So the functional form of A is this. Wow. So we actually nailed it just with that one substitution. That's, I say that as though I am surprised. It's funny because I am always surprised. I've done this before several times, right? But I'm always kind of surprised that it works. It's like, oh, wow, look at that. A is, we got A from all this mess, man. Look how bad this thing started. And yet with this, who knew? Who knew? Wow, look at that. A did this. I wonder what Mr. Schwarzschild felt like, in the middle of the war when he said, oh, look, I can figure out what A is. That's surprise, surprise. I guess, you would think that a spherically symmetric system, you might imagine, look, this can't be so hard, and you'd be motivated to keep beating back. I can imagine, the way you would think about it is, look, it's spherically symmetric. There's no way this can be a very complicated answer. The metric can't be some unfathomably sophisticated set of functions. That means there is a way to simplify this radically. I just got to keep looking until I find it. And then he does. The other thing, too, is people were just better at math back then. Back then they had no computers to waste time with numerical methods and stuff like that. So he may have looked at this right away, and his algebra was so darn good, he immediately saw his algebra basic calculus is so good that he just saw right through this immediately. It'd be fascinating to know. Just how did he get there? I'm sure if I read his original paper or something, it might be insightful, but just a curious thought. Okay, but we've solved for A. We now know what A is. That's great. A is this thing right here. Well, now what is B? Well, B is not very difficult when you remember that A times B was a constant. So I'll call that constant, let's see, I need a third constant now, right? C3. So this means that C3 divided by A minus C1 over rho plus C2, that has to equal B, right? This is C3. So I can take C3 into the denominator, right? By, I just divide the top and the bottom by C3. Wait, this equals B, right? This equals B. Let me get that straight. This here equals B. So I take C into the denominator, and I should get 1 over, let's see, this will be, I think it looks something like this, right? And now you just recombine this. This is basically two constants that this ends up being. So we write B in some final form is 1 over one constant, I'll call it C1, CA minus CB over rho, right? Because you basically end up with these constants, because this product, this isn't introducing a new constant really, because they can be combined with these other arbitrary constants to give you this object that has two arbitrary constants. But that's what B is. And it does have the right properties, certainly not dependent on time. And it is obviously B times A is going to be a constant. So that's good. Now it is true that, well, we still have to figure out what these constants are, but we know the form of A and we know the form of B. So problem is virtually solved. The final piece to all this comes when we rebuild the metric from our new information. Right? I write G mu nu. Well, first thing I do is I write, we write the line element, right? The line element is our thing. ds squared equals the 0, 0 term. That was the A term. So it's minus this guy. It's got to be minus A. So I guess we can look at the first one. So this is the line element, and that's where A sat, and that's where B sat. So A we now have as C2 minus C1 over rho, right, which is sort of what this thing was. That minus sign here comes from this minus sign there. So we do know that in the weak field limit, when rho is really, I'm sorry, we should say in the far away limit, the boundary conditions are what's going to give us these constants. So when rho is really, really large, regardless of what C1 is, this term is going to drop to 0, leaving only behind C2. But when you're really, really large, this thing has got to become Minkowski, and the spherical form of the Minkowski metric, A is 1. So right away we know that C2 is 1. So the other thing we remember from the Newtonian limit was that G00, right, has to equal minus C squared minus or plus 2 times the Newtonian gravitational potential. And of course, then that is, in our units, it's going to be minus 1 plus 2 gm over r, right? Minus 1 plus 2 gm over r with a negative sign. right? There's the potential is negative, right? So that is our Newtonian limit. So clearly this here is C1. The C2 is already established by the sort of the long range boundary condition. But the weak field boundary condition is this guy. And that's where this M comes in, which is interesting, right? So there's this M is the Newtonian limit is what drags in this idea of mass, right? Because remember, we're in the vacuum. So there's no mass or energy in the classical vacuum that this whole thing is being done in. Remember, I'll remind you that this is the exterior solution. So this solution is all outside of our dense gravitating body. But because we know that there is gravity and we know that it has to hit this Newtonian limit, this Newtonian limit is where M comes in. So M represents, we know what it represents classically. It classically represents mass. And the only possible mass it could mean is the total mass in the center of our system. But as far as the exterior solution is concerned, this is just some sort of mysterious magic number out there that is causing, for some reason, is causing space-time to be curved, and the flat or the unoccupied space-time is being bent to sort of match the boundary condition that exists here inside the star, right? So the star actually has a no-kidding G mu nu equals 8 pi T mu nu, where this is a real thing. So you would think, oh, well, the space out here only knows about this because the space-time curvature out here has to match the curvature inside through boundary conditions. And essentially that's what this is telling you, is that somewhere it knows, out here, it knows that there's a mass somewhere with some boundary condition that it all ties together, but we need to know what this mysterious number is so we know how much bending is done out here. And I'm speaking anthropomorphically, but that is sort of what's going on. This is where mass enters the vacuum solution. It's through this Newtonian limit is how it appears in there, which is really, I think, fascinating. Now, B, the same process can be done with B, right? In the far away, to match the flat space boundary condition far, far away from the gravitating body, way, way out here, where rho kills CB, this thing has to be 1, right? B, the value of B has got to be 1 far away, which means this constant here, CA, is going to be 1. So that gets us to 1 over 1 minus CB over rho. Oh, I just noticed, by the way, this R really should be a rho, right? The radial coordinate in this system is rho. And then we look at this thing. This is A, and this is B. Multiplied together, you get this. The only way this can equal a constant is A has to equal B, right? It's funny, that's not totally obvious, but imagine that they were different. Imagine A was 1 and B was 2. When rho is 1, then this thing is 0. But when rho is 2, this is 1/2 over 0, which is like, wow, when rho is 2. Well, that would be a drag, right? This is infinity, but it's clearly not constant unless those two are the same. So the constant here in B is the same as the one here in A, and that solves the whole thing. So the ultimate answer is, and we'll just go to the catalog for it. Well, on our way to the catalog, we'll stop here. We can now substitute in for A and B dot, right? We now know, for example, that A and B dot are 0, right? So all of these dot terms are 0, but we can substitute in for that, and that by taking the derivative with respect to rho, no sweat. And we get all of those derivative terms for the metric. But more importantly, we can go back to, where was it? Here. The metric itself. We substitute right in for A and B, and we've got it. We've got the metric. And that Oops, sorry, that turns out to be, let's go to the catalog of spacetimes. There's the Minkowski one. Hold on. Yeah, here it is. This is it. This is the metric we just solved for, right? We just calculated this guy, and you'll see that it's exactly the same. Now, they take 2gm and they create a constant out of it. First of all, the c-squared is a unit conversion thing. That happens because they're keeping all the factors of c squared. But this they call the Schwarzschild radius, and it's really important because this term here goes to 0 at the Schwarzschild radius, and this term goes to infinity at the Schwarzschild radius, which is an important point for a later conversation. But that is the way that is the metric in these coordinates, right? And we can change coordinates, and this singularity will disappear in a different coordinate system. But when r equals 0, then this blows up, right? And that singularity you cannot remove, right? So the point is we have now solved for this, right? We've gotten the answer, and we worked it all the way through from the very, very most basic piece. So interpreting the answer now becomes the next mission, right? We want to now, in principle, we would want to study the Schwarzschild system. Ironically, we did a bunch of that earlier. I actually plotted all the geodesics of this space-time. We did all that work calculating the geodesics. We assumed we knew the metric, and we calculated the geodesics. In this case, we did it the other way around. We started with the Einstein equation and calculated the metric. And some of the non-Newtonian stuff was made by assumptions regarding Newtonian limit of the geodesic equation. So we kind of hit this from both sides. I'm going to kind of do a recap of the course next, but I think this this is a good place to stop on this lecture today. This is pretty exciting. I really like solving this thing. I wish we could solve more of them. I wish I had the tenacity to go through other solutions. I guess there is the one question that is remaining, and that has to do with the boundary conditions. Maybe we should talk about that for a second. All right, so you remember how we did this. We set up g mu nu rho theta phi. And look, I got rid of the t. The t doesn't belong, right? It's not a function of t. So interesting there. And then this is the exterior solution that we just got. And this is the interior solution. And the idea is that at some Schwarzschild radius rho, now notice that's called the Schwarzschild radius. I shouldn't say that because the Schwarzschild radius is a specific thing that has to do with event horizons in the black hole. What I meant is the radial coordinates in the Schwarzschild coordinates, the radial coordinate, which is called rho, which I'm distinguishing from the radius away from the center, r, because since b does not equal 0, the radial distance from the center and the Schwarzschild coordinate label of a point, right? That's what's going on here. There's a point here on the boundary of our star. Those are different numbers, right? So anyway, the coordinate label of a point on the surface of our gravitating body is located, say, at a distance rho 0, right? That's the radius of our gravitating body. And when I say the radius, that's risky because, again, you start thinking about lengths. What I should say is that is the radial coordinate of the boundary of our gravitating body. That's the radial coordinate. So now the metric, the interior metric, g mu nu at the radial coordinate phi 0, theta, and phi, this is now a function of two variables because I've plugged in a constant here, so all that's left now is two variables. That guy has got to equal g mu nu rho 0, theta, and phi. That's matching the boundary condition between the exterior and the interior, right? The interior. So we haven't done that, right? We have matched the boundary condition the other way, right? Way out here, far away, the boundary condition there was g mu nu has to approach eta mu nu. in some coordinate system. So I'm assuming this is in spherical coordinates, right? So G mu nu in the coordinates we have has to be this approach eta mu nu in spherical coordinates. So that we did that. So check on that boundary condition. The problem is the interior boundary condition. So what do we need to know to solve the interior boundary condition? Well, first of all, this is a complete cop-out right now, but we need to know our rho 0. So you give me rho 0, and I work out the interior solution, and then I take that interior solution and I match it with the exterior solution. Now, it didn't seem like there was a lot of room to play. It seems like we pretty much nailed down the Newtonian limit thing, kind of fixed this guy. But ultimately, I can make rho as small as I want. In other words, I can make the exterior as big as I want by making rho as small as I want. And I can always delay establishing that boundary condition, right? And ultimately, that's what we do, right? We just say, you know what? We're just going to let rho get really, really, really small. And ultimately, we're not going to worry about the boundary. The boundary condition is going to be at the point rho, not r, rho equals 0. And at that point, of course, the classical equations kind of break up and blow up. And so there's a lot of questions about what that means, but we haven't really sat down to interpret the Schwarzschild metric solution yet anyway. And I'm not sure that we're going to do that in this sequence of lectures. I'm much more interested in the fundamentals as opposed to the applications. Although there are a few applications I am really interested in covering. But regardless, we're not missing, right? If we were missing some constants here, then we'd be forced to match the boundary conditions in here. But we're not missing any constants. We've got them all pretty solid. The fact is this metric doesn't make sense at the boundary. And that is another thing that's keeping us from having to solve the boundary condition. You can't set this. There is a value of rho. I shouldn't say at the boundary. There is a value of rho where this thing blows up so bad that it's really questionable what's going on. So even setting up, in other words, there's that Schwarzschild radius, right, where G mu nu at that radius is ridiculously big. So if the star's surface is underneath that, right, then you can't really even get there to match the boundary condition. You already have a big problem that you're staring down. On the other hand, what's more likely is that the surface of the star is bigger than the Schwarzschild radius, right? So matching the boundary condition under those circumstances is something you should have to do. And what you basically say is that, you've kind of got it. We know that the totality of what's inside here, let me boost my pen again. The totality of what's inside the radius of the object, all that stuff has a mass of m. Whoops. A mass of m. Let me get my thickness back down. Some mass m. And that's really all you need to know. And then you just need to understand that you can't use this metric inside rho 0, right? It's no longer valid inside rho 0. But the way we're dealing with it is we're just pushing this thing away and not dealing with the interior solution. We're going to assume that we have an infinitely dense, infinitely small point, and that's the singularity. Now the question is does physics allow this, right? How physically accurate is this idea? And surprisingly, there's a considerable body of thought that says, you know what, that is pretty physically accurate, right? There's no known physical mechanism that can support a star against gravity if the radius of the star is small enough, and evidently the radius of things can actually get that small. So that's why we believe that there are black holes out there, right? So these black holes actually do satisfy all of this. There is this infinitely small point in the classical theory. Now, presumably, what happens at that infinitely small point is under hot debate, right? And that's where quantum gravity would come in and change things and modify this classical theory in a way that would prevent, some sort of infinite singularity inside the black hole. But even if it does or it doesn't, we'll never see it because no advanced theory argues that you can really get inside and observe what's inside the black hole anyway. So there is a certain philosophical question about whether or not the whole issue is moot. Not my battle to fight. But anyway, there's nothing missing because we didn't really deal with that boundary condition. Okay, so that ends our discussion of the solution of the Schwarzschild geometry. So the next lesson will be a bit of a recap of the whole series. It'll be the last lecture for the series, and we'll discuss topics that we haven't touched on that we may come back to topically with individual lessons.